In this video, we will see or we will discuss the OFDM, the key aspects of OFDM. The details we have already discussed, but a quick summary is given in this video. OFDM stands for orthogonal frequency division multiplexing. And in OFDM, if total available bandwidth to us is capital B, then we subdivide it to multiple subcarrier in such a way that the separation between the subcarriers is B by N. So this is the separation. Similarly, so this type of carrier assignment is also possible. I think in class I discussed in different way, but this is also possible. So this is the easier way you can remember this, that these are the, if the total bandwidth available to you is B, then we divide our whole available bandwidth to N subcarriers, and each of the subcarriers can be like this, right? Where I is from I0, 1, 2, minus 1, minus 2, and so on until it consumes the complete available bandwidth or covers the complete available bandwidth. So this is the carrier assignment which we have seen, and thus our multi-carrier signal or OFDM signal becomes baseband of the OFDM signal. If you remember, the baseband part can be written as SI, the complex coefficients e to the power j 2 pi fi into t. So this is the baseband of the baseband equivalent of OFDM signal. I have told you how we can see the baseband and passband equivalence. This we have already discussed. Just replace fi here. So we get SBT, the baseband equivalent of OFDM or multi-carrier signal. I am calling it multi-carrier until we convert it to DFT, IDFT form. We generally call it multi-carrier. So it is a multi-carrier signal, and we put here SI e to the power j 2 pi FC plus. So just take this part because we have already seen that all of this maths. So just take this part so that it is called baseband. So write B band. This all we have discussed, right? This real part, etc. That I am not going to look it again. Just to quick summary, just you put this part, right? The frequency shifted by FC so that it is in baseband. Since we are discussing the baseband, this is the baseband of the OFDM signal, and then the multi-carrier signal. Then we sample this at each TS, and TS is equal to 1 by B. So just note it that TS is equal to 1 by B. TS is equal to 1 by B. The total available bandwidth is equal to 1 upon the total available bandwidth is TS. So SI e to the power j 2 pi capital I B by N. So if you write T is equal to mu TS and TS is 1 over B, or you write TS, and from here TSB is equal to 1. So this and this will become 1 multiplied. When we multiply these two terms, it will become 1 power I mu by N. So this is what we have seen, that how a multi-carrier signal, the samples of a multi-carrier signals, this we represent by S mu. So the sample of this multi-carrier signal is the IDFT or DFT of the, this is the DIDFT. This is IDFT formula. If you remember from your signals course, that is the IDFT formula. So if you write it nicely, you just take all the samples. How many samples? You sample it sample at each TS, and the duration of the multi-carrier signal is 0 to n TS, if you remember. So how many samples we will get? N samples. So just collect all those samples. Just call this as a baseband OFDM samples, and collection of all the complex constellation points as the capital S vector, complex constellations, right? So what is the relation? That S is IDFT of S, or vice versa, that S is DFT of S. So just let us quickly see how the block diagram of OFDM look like. These are the data bits. So first we convert the data bit to constellation points, right? So data to constellation mapping, and all of these constellation point, before this we just put a demux so that we can collect few bits, and these bits are feed to the bits to constellation mapper. So you will get a collection of all the complex constellation points which you want to send. All the information is here because you are mapping your information bits to constellation points. So all the information in the constellation points. We perform IDFT of these constellation points. So we will get the samples of the OFDM signal. How many samples? Of course, n. Then before converting it to analog form, because this is in digital form, before converting our OFDM samples to analog form and then transmitting it, we put a cyclic prefix before it. We will just quickly look at this in later. Just write cyclic prefix, we add cyclic prefix. So once we add the cyclic prefix, this is with cyclic prefix, you can call it x1 for example, or tilde. So this is the new OFDM symbol vector. So these are the samples of OFDM signal. This is the OFDM symbol also, sometimes it is called OFDM symbol. This is the OFDM symbol with cyclic prefix, and then we convert it to DAC, provide DAC, and we convert it to analog form, and we modulate it over in the RF, and we transmit it through the channel. And once we transmit it, all the inverse process will be performed at the receiver. What would happen at the receiver? Antenna will receive your OFDM symbol. There will be a RF demodulator, or it is also, you can think as a baseband to passband converter. Here it will be an ADC which will provide again the samples as tilde. S tilde is cyclic prefix along with the S. So since cyclic prefix you have to remove. So here we remove cyclic prefix because all the information is only in S, right? We are adding cyclic prefix because of some reason. We will discuss this later. Then once we remove CP, we get S only. We have removed CP, so we will get S vector only. S vector only, which has all the samples of the OFDM signal. Then we just, what we'll do, we will perform quick DFT, and it will give you all the constellation points. And then what we will do, constellation to bit mapping, and it will be provided to a mux, and all the information which you have transmitted will be received at the receiver. So let's quickly see why do we, or what is cyclic prefix. So in OFDM symbol, if this is your OFDM symbol duration, there are n symbols, S1 up to Sn, and duration of OFDM signal is nts. So what we do, if we pass, when OFDM signal is passed through a wireless channel which is a wireless channel passed through a wireless channel which is modeled as L delay line filter. So in order to avoid the inter-symbol OFDM interference, because this will be your previous OFDM symbol, you can represent it by some previous minus 1 1 as previous 2. So this is your previous OFDM symbol. It does not interfere with the current symbol. What we do, if the channel is L tap, then we just map the L minus 1 samples, and the L minus 1 sample is just copied and pasted here, L minus 1. Therefore, the length of your new OFDM symbol which you have represented by, you can call it SP with cyclic prefix. So your S with cyclic prefix S with cyclic prefix, the length is N plus L minus 1 into, and duration is TS. So N plus L minus 1 TS is the duration of the OFDM signal with cyclic prefix, and it is done to avoid inter OFDM symbol interference. Now let's see how our OFDM signal looks in time and in frequency. But I mean, this is your OFDM signal which is coming out, right? OFDM signal, baseband, and this is passband. So how this looks over air? So it's better to write it here. So how your OFDM signal is in the air. So as you can see that this signal is collection of OFDM signal is collection of all these samples, and each sample we get when we perform this type of operation, summation of this, that S1 will be summation of I Si e to the power j 2 pi I, mu will be 1 upon n, and I, we have to sum it up, right? Because so therefore this value at each time instant, sometimes it might be less, sometimes it might be high, because some of these components will be in phase and some of components will be out phase. So what would happen, your OFDM symbol will look like this, and few times the value will be very high, and then this. Make sure that this part which is corresponds to L minus 1 TS, and this part is must be look same. So just let's do it here, and because we are copying the last L bits or L symbols, so L minus 1 TS. So initial part and this part will look alike, and sometimes the OFDM symbol will be have very large values, some of the samples, some will have low values. This is why OFDM suffers from peak average to peak power ratio, high PAPR, high peak to average power ratio, high peak to average power ratio. It means on average the power will be low, but sometimes there will be some peaks where all these signals, all of these signals will be in phase. All the signal which will be in phase. Or you can think like this: you are sending signal to multiple frequencies. So this is one frequency, this is another frequency which is fast, this is another frequency which might be slow. So what would happen when you sample it at ETS symbols? Some of the point will be in phase, some of the point will out phase. So it might happen that when you sample, some of the sample will have very peak value, right? And how your OFDM signal will look at the frequency domain, you can see like this. As I told you that you divide your whole available bandwidth in various subcarriers. So C plus 2B by N, various subcarriers, and each carrier will carry information. So this carrier will like this, this is the another carrier, and this carrier will be like this, because each carrier will have its first null at 1 upon nts, because each of the carrier has length or time duration nts. The first null will be at 1 upon nts, and if you remember, our 1 upon ts is b, therefore at b by n this will be its first null. Similarly second, and if this is third, then this is the main lobe, and there will be some side lobes. Similarly the side lobes, and each side lobe will be of duration 1 over nts, right? Because each of the signal will have nts duration, right? So this is frequency fc plus p by n, fc plus 2b by n, and so on. This yellow part will also have some side lobes. So this is how your OFDM symbol will look in frequency domain, and this is how it will look in time domain. So confused, in our class we have discussed that this is this single carrier. In single carrier we transmit bits like this. So this was the timing diagram to show the boundaries of each. This only discuss the boundaries of the single carrier versus multi-carrier signal. It was not the waveform of the OFDM. So just be. So this is how we discuss the timing diagram of single carrier versus multi-carrier signal. So don't confuse this with the waveform, OFDM waveform. Thank you.